Yeah, we'll continue from there onwards. We discussed previously on isosilicates and sorosilicates, right? Also, we have to now continue with the other types of silicates, that is cyclosilicates, right? Inosilicates and phyllosilicates, and also tectosilicates, right? The remaining sections. So we will continue with those, and you can see clearly the nesosilicates are individual tetrahedrons, and sorosilicates are joint silicates with two tetrahedron with a bridging oxygen. And cyclosilicates, today we are considering the cyclosilicates, which are like a ring structure, okay, like a ring structure. So you can see sort of hexagonal and orthorhombic structures are there, the symmetries are there, but they seems to be like hexagonal, but it's not real hexagonal. So therefore it's called pseudo hexagonal. Okay, it's called pseudo hexagonal because it looks like hexagonal, but it's not real hexagonal. Normally these silicates are having moderate densities from 2.6 to 3.2 like, and hardnesses are varying 7 to 8. That means a little bit hard. For example, beryl is one of such examples, and they have prismatic habits, and the cleavage is not present very well. So they have a poor cleavage. In some cases only you can see some cleavages like here. Okay, otherwise they are not having nice cleavages, right? So it, in a crystallographic point of view, they look like this way, but it's a little bit complicated, this image, but you don't need to focus much on that because you will learn about these things later on in your next years. So you don't need to focus much on that, but just keep in mind that these cyclosilicates are ring type silicates. That means ring structures are there. So you can see they are joined in form of a ring, right? So there is no specific number of tetrahedrons to join, but however they should be connected in a ring manner. Okay, so here you can see 3 silicon tetrahedra, here 4 silicon tetrahedra, and here you can see 6 tetrahedra. Okay, right. And beryl is one of the common example that we can consider under these cyclosilicates or ring silicates. There you can see 6 silicon atoms are there. That means 6 silicon tetrahedrons should be there, right? So clearly you can see here they are not present with a very clear cleavage. So we said that they are having poor cleavage, but some cases there might be some good cleavages present, but hardly, right? But these are crystal phases. Okay, these are not cleavages, they are crystal phases. You can clearly see their symmetry here. They are crystal phases. And corderite is also considered to be a cyclosilicate. Corderite is also a very common mineral. You will learn in the next semester under introductory petrology lectures. Okay, it's a common rock forming mineral. Rock forming minerals means the minerals which are contributed to form different types of rocks, right? Igneous or metamorphic, whatever. The most common type of minerals are called rock forming minerals. But like beryl like minerals, they do not contribute much to form rocks, right? They are found in rocks as accessory minerals. Accessories means the minerals which are found in very low quantities, low abundances, and which are not essential to form a rock, right? In a formed rock, you can find that, but to form a rock, you don't need that particular mineral. But for rock forming minerals, depending on the protolith means the parent materials which contributed to form the rock, must have different types of rock forming minerals, right? So if the protolith is high in iron and magnesium and aluminium, okay, iron, magnesium, and aluminium, then your rock will be rich in minerals like cordierite. Okay, so that is the story behind that, about the rock forming mineral. Tourmaline is again an accessory mineral also, which is a gem mineral, like beryl. Beryl is also a gem mineral, and they are found in pegmatites, mainly pegmatites. Okay, do you know pegmatites? What are the pegmatites? How do you understand the type of rock, a pegmatite? Any idea? Yes. What is the main? What one of the main features of pegmatites? Probably you may have heard that a lot of gem varieties are found in pegmatites, and people like to mine gems in pegmatites. There is a reason for that. Any guess? No. Pegmatites means large grained or very coarse grained rock. Okay, igneous rock. So their grain size is very big, even some tens of centimeters, maybe big size, very big size. Unlike other rock types where you see very small minerals, right? Sometimes you need a hand lens to identify the minerals. They are so tiny. But in pegmatite, the some grains are there in very big size, maybe 5-6 inches big, right? Some beryls are there, very long crystal, lengthy crystals like that, right? So those are pegmatites. So gem varieties are mainly found in that such kind of rocks. So people prefer to have bigger gemstones because they are having a higher value. So that's why people try to find gems in pegmatites. Okay, tourmaline is also a gem variety, and which belongs to a cyclosilicate group. Okay, and as you see here, the chemistry of tourmaline is very complicated, right? Very complicated, and you can see it contains boron, the element boron. So this is an essential component for tourmaline to form. If you don't have boron in your protolith, there will be no tourmaline, right? Whatever the other elements are present, doesn't matter. It should be having a boron, right? So we call it a borosilicate. Okay, a borosilicate. So silicate, which is boron is joined into the structure. So for example, here you can see the silicon aluminum atoms, and silicon tetrahedra is here, and other atoms are joined to that structure. For example, aluminum, those are essential ones. But you can see here beryllium is also there, right? So likewise, boron is interconnected into this structure, right, for tourmaline. Otherwise, it will not form tourmaline. So it's a borosilicate. It's a special type of silicate. And some tourmalines are having a structure or texture like looks like watermelon, right? Green and pinkish or reddish stripes there, right? It looks like a watermelon. So then it's called a watermelon tourmaline. It's a very characteristic feature, but it's very rare. Okay, so these are the commonest types of cyclosilicates, uh, which you can find in most of the rock types that we have. And I said, I think in the last lecture, that I am not going to give you all the list of uh, minerals that belong to each and every group. Okay, so you will have to find the other minerals, and you have to submit an assignment, which I will give you sometime later. Okay. Right. So that's about tourmaline. And then we will move to inosilicates. So you can see here, we just considered cyclosilicates or ring silicates. That means they are joined in a ring pattern. Okay, and these are just two tetrahedra. They are joined together with the bridging oxygen. Okay, just a single bridging oxygen is there to join them together. And mesosilicates are isolated tetrahedrons. And then we have another thing that is called inosilicates. Okay, inosilicates. Inosilicates are two types. Okay, so you have another type of inosilicate here. Uh, One is having a single chain. Okay, they have only one chain, but the other one, you have there are two chains. So there are two chains. So single chain inosilicates are there, and double chain inosilicates are there. So they are different in chemistry and structure and everything, although they belong to one silicate family. Okay, right. These are chain silicates, which you can see here clearly. They are having uh, two types of structures. So one is a single chain inosiliate, which we call pyroxene group. Okay, pyroxene group. So they are having this particular structure, Si2 O6, and metal ions are there, right? Two metal ions are usually joined. More than that can be joined, but basically two metal ions are there. And double chains, they are called amphibole group. Okay, they are called amphibole group, uh, and they are having Si8 or 22 structure. The chemistry, okay, formula. For that, these tetrahedrons, silicate tetrahedrons, more than two uh, cations are joined essentially, right? So you have at least three cations joined. Even more than that can be joined, right? Replacing each other. So we'll see that also later on. But basically, in the basic formula, what we refer is having three cations. Okay. In addition to that, there is a very special feature for these amphiboles or double chain silicates. You have OH group as well. OH group and fluorine or halogen group. Right. Previously, also you saw some OH joined with, for example, tourmaline or so, but it's not essential here. Even without OH group, tourmaline can be there, and without OH group, right? Even cordyite here without water, and actually this water is just like stick into the structure, right? It's not the part of the structure because we call them adsorbed water, right? Adsorb, not absorb. Adsorb, ADSORB, adsorbed water. It can be easily removed by very gentle heating. Okay, so and also it's not essential to have in the structure. That means if no water is there, still cordyite can be formed, right? Like same as tourmaline. But The case is different for double chain inosilicates, where this OH is an essential component. Without OH, you can't have amphiboles. So we call this particular group as hydrous mineral. Okay, this is a hydrous mineral. So the reason is OH group is interconnected to the structure. In addition, in some cases, there can be a halogen ion also there. Chlorine, like halogen, can be connected to the structure. That is also possible, right? It's not essential, but water is essential. OH is essential, but usually halogen is also there, right? If you analyze a particular amphibole, definitely you will find either chlorine or fluorine in their structure. So single chains are pyroxenes and double chains are amphiboles. Okay, and they have both monoclinic and orthorhombic symmetries. And these pyroxenes or single chains, they develop very clear or very characteristic, approximately 90-degree cleavage. So you may have seen some images under microscope or some photos of the minerals, right? Pyroxene, for example, there are cleavages nearly 90-degree, right? So like this, actually it's like 88, 86 to 89, like, right? Two sets of cleavages. So that means you may have this type of cleavage sets, two sets. Oh, sorry, it's not. Okay, anyway, just like this, right? Two sets are there. One set is here and the other set is here. Okay, right. And in amphipoles, they develop 120-degree cleavage. So 120-degree means it's like if you have one set of cleavage like that and another set is like this. Okay, here 120-degree. You may see this type of cleavages. Okay, so this is how you can easily recognize them under the thin section. When you see them, even in the hand specimen, you can see these cleavages. Okay, they will break accordingly, like 120-degree angle, right, in amphiboles. So pyroxene structure is here. So you have Si2O6 structure, and here Si8 O22 structure, right? So it's you can count these oxygen atoms, and you can count the silicon atoms as well, right? So they join together like this. Okay, so that it forms a chain. So it continues like this as a single chain. So pyroxenes are single chain and amphiboles are double chain inosilicates. And so it's like usually these tetrahedron chains, they run parallel to the z-axis, right? You know, in crystallography, you may remember you have axis. The long axis is called z-axis, right? Either c or z, right? Z, right? Z or z, or you term it as c also, right? So along the c-axis, you have this which is chains are formed. And these pyroxenes are divided. So this is important, this part, okay, very important, because it's a new part, because you know the crystallographic sections already, but the section that I am now going to present you is a new part for you, right, under descriptive mineralogy. So monoclinic pyroxenes and orthorhombic pyroxenes are there, right? So in monoclinic pyroxenes, we term them as clinopyroxenes. Monoclinic, clinic, that means it's one mono is one, clinic is inclined, like it comes from that word. Okay, monoclined, like its one axis is inclined. That's the idea, monoclinic. So clinopyroxenes, they have one axis inclined, and we term them in a group as CPX, clinopyroxene, clinopyroxenes. And we have a series of these minerals, a family, like, right? So we call it diopside Hedenbergite series. So one side is diopside and the other side is Hedenbergite. So two compositions. So these are compositional end members. So I think I mentioned in the story about end members in the last lectures, which I referred as solid solution, right? You remember solid solution? So two sides or two compositional sides. So one side is uh, uh, one composition and the other side is another composition, right? So the extreme ends we call end members. Okay, so we have a series like that. So diopside Hedenbergite series. So like this, right? So the minerals which fall uh, here is 50% mark. Okay, minerals which fall below 50% of this particular composition is called diopside, and minerals which fall like here, that means greater than 50% should be from this component. Those are Hedenbergite. Okay, so we'll see this diopside Hedenbergite composition in terms of a compositional diagram. So for pyroxene, we draw compositional diagrams uh, as a triangle, right? So why we use a triangle means you know the common structure of pyroxene is XYZ. Sorry, XY is it 2O6 means silicate tetrahedra. This is silicate tetrahedra, and this one are the cations. So what are the cations you have? You may have in the structure, right? Previously also we considered the same XY silicon tetrahedra. Okay, for pyroxene. So what are the cations possible? So these are the X cation. Actually, there are crystallographic sites. You will learn these things, I think, in your coming years, not now. There are sites we call M1 site, M2 site, like. So you see here in the crystal structure, there are different places, right? These different places have different sizes. Okay, so some cations should fit into these sites specifically, and all the cations cannot occupy any site, right? For M1 site, it has a specific size, right? So it has a specific site, so it can fit only some of the cations only, right? For example, for M1 site, manganese, ferrous, magnesium, ferric, chromium, titanium, this one can be fit into those sites. Okay, and M2 site, it's here, it's a little bit bigger. The X cations, right? M2 site fitting cations are sodium, calcium, manganese, ferrous. Again, some ferrous and magnesium can also occupy there, right? So, but some other cations cannot occupy, right? For example, sodium, calcium like cations can occupy only in X, but iron, manganese, magnesium can be occupied in Y also, right? So such differences are there. It depends all on the amount of the atoms available in these different cations, right? So that means the concentration. Concentration matters for that. Okay, concentration matters for that particular composition, right? That means if you have some cationic iron cations in abundance, for example, iron in abundance, so they occupy both sides. So fully occupy in one side, which is M1 side, and the remaining amount will be assigned to M2 side, like, right? So like that, there are such different different cations occupying different sites, and depending on that, the structure is defined. Okay. So you can see here, for example, more than two cations are there, right? But usually pyroxene is formed in the basic formula. You can see only two cations we represent, X and Y. But it can be another one cation can be replaced with X or Y, right? Instead of X, for example, if X is sodium, uh, some amount of sodium can be assigned into some of these relevant crystallographic site, but there is possibility for another cations to jump into that site, right? For example, calcium can jump into that site, remaining sites, available sites. So in that case, you have uh, three cations, right? But still, those cations are selected from that particular X group only, right? So sodium, instead of sodium, some places calcium can be there. The reason is all depend on their ionic radius. Okay. If the ionic radius fits, then another cation can replace these ones. So in that case, here, if sodium is there, then there is possibility for calcium also to come into there. So you have another cation. And then for Y, you have again another cation, for example, maybe iron, right? Iron, so iron can be there. Okay. And also in some places where iron can be occupied, magnesium can also be fit into that, right? Instead of iron, there can be some magnesium also. So in that case, you can have magnesium also into gone into this site. But basically, these sites are they should fit into the crystallographic site, right? Although there are two ions here, both belong to what? Y family. Okay. Y. And here you have another group, X. Okay. So by this family, X is represented, which is shown here. Okay. And by this Y family, this is represented. So basically, the requirement is satisfied. So therefore, it doesn't matter, because to replace this iron and magnesium, both should be of similar size. So therefore, there will be no distortion for the crystal. So that's why. Okay. The ionic radius matters for that. So whatever ionic radius and valency also matters, of course. Actually, radius and valency ratio is also important. That's why valency and ionic radius matters. Right? You will learn these ones in the next years in detail. Okay, and also in petrology, you will learn a little bit on this. Please give me 5 minutes because there is one exam issue going on in the department. Today, Geology of Sri Lanka for third years doing. So please wait a few minutes, 2 minutes may be enough. Okay, let's continue. Right. So basically, XY is the formula, but this XY can be replaced by one or two similar group ions. Okay. Right. Just keep in mind. So that's why we take uh, a triangle to represent these compositions. So here I think you can clearly see this triangle. One side is magnesium. Okay. Can you see this magnesium? One side. Can you see the diagram well? Please let me know. Otherwise, I have to. Is it iron, magnesium, calcium? Can you see clearly? Just tell me quickly. Somebody.
Yes, sir.
Okay, right. Magnesium, iron, and calcium. So these are triangular representation. Why we use triangular representation is mainly we have magnesium, iron, and calcium, which are replaced in these pyroxene structures. Okay, so basically we have calcium, iron, and magnesium. Even sodium is not that much, right? But there is a separate group for pyroxenes which have sodium abundantly, which we will learn after this. Okay, so for the time being, you consider calcium, iron, and magnesium as the main components that we have to consider in defining pyroxene structures. Okay, so calcium comes from X side for M2 assignments, and Y for Y we have iron and magnesium. Okay, right. So we have iron, magnesium, calcium representation, and this particular series that I am talking about, monoclinic pyroxenes, that is clinopyroxenes, they are having diopside Hedenbergite series mainly, right? So diopside Hedenbergite series means in this range, okay, in this range. So this is the very common type of clinopyroxene series or the compositional range where in natural environments we find this particular inosilicates. Okay, so diopside means this composition, calcium and magnesium composition. Okay, Hedenbergite mean calcium and iron composition. That means in the structure, mainly you have calcium and magnesium, and then silicon tetrahedra. For Hedenbergite, what you have is calcium and iron, no magnesium. So that's why we call them N members. So for Hedenbergite N member, it's definitely rich in calcium and iron, and for diopside N member, it's rich in calcium and magnesium. Okay, so those are the two N members. So in between, somewhere here, like for example 50-50, there can be magnesium and also iron. Calcium is found in equal quantities because the distance from here to here is equal. From this calcium end to this line is equal in this place. So that means calcium amount in both in calcium amount in this particular composition which fall in this range is equal, right? Iron and magnesium are 50-50. Okay, iron and magnesium are 50-50. Also, calcium is also like close to 50 because it's in the central part, right? If you divide this calcium line, you can divide it into 50-50, right? So calcium, magnesium, iron, all are equal amounts, right? If you take calcium and iron, calcium and iron only, then 50-50. If you take calcium and not calcium and iron, magnesium and iron, they are 50-50. If you take calcium and magnesium, they are again 50-50. right, like this. So you have to keep in mind that if we have two component composition, right, like this, if you have a suppose you have a component and b component, right? So along this line a and b varies. So a is 100% a here, 100% a, and here 100% b composition, right? So if you take somewhere like here in the middle, so you have 50-50 a and b, okay? But if you have another component in this structure called c, right? So then a little bit complicated, then it becomes a triangular representation, right? That's why we draw a triangle. So you have a triangular representation, and but still along this line here, C is 0, right? There is no 0 because C 100% is here, 100% C is here. So if you take a line like this, uh, here you don't see any C, right? It's 0. For likewise, similarly, the point here, okay, in pyroxene triangle, the point here, if you have any composition, there calcium is 0, okay? But in the intermediate places like here, you have calcium close to 50% or so, okay? So anyway, this 100 should be divided in by three component. If you have three components, so that means so you then only you have almost equal amounts of quantities in a composition in between, right? Somewhere here, okay, right? 30-30 like composition. That means from here and from here you have to draw lines to take the composition of these ones, right? That will represent here. Okay, right. So now for this particular group, monoclinic pyroxenes or clinopyroxenes, we have one very common series which is called diopside Hedenbergite series. So in between, somewhere here, we have a composition called ogite or ogite, right? That is also clinopyroxene, type of a clinopyroxene. So it has a some kind of a bulky right, so what do you call it, it's a curved compositional line, right? Why it's curved unlike straight line here? It's curved because this ogite, particularly relative to diopside and Hedenbergite, are having less amount of calcium and high amount of iron and magnesium. So iron and magnesium is downwards now, right, towards this side, iron and magnesium, okay? So therefore, if since the iron and magnesium are a little bit higher, they should go towards, the line should deviate towards that side. So that means the calcium becomes more distant, right? Calcium line become more distant. That means calcium is less. If calcium is high, then it should go like this, no? Right, like that, right? But there is no such uh, indication here in this diagram, okay? So therefore, ogite composition a little bit deviate from this diopside Hedenbergite line. So therefore, for the ogite composition, it's a little bit iron and magnesium rich, right? But we consider it as a single series, okay? So, but still we take it as a single series, okay? This whole composition is taken as a diopside Hedenbergite series, but in middle you have ogite composition which a little bit deviate from typical deviate from typical diopside Hedenbergite series by having high amount of iron and magnesium relative to diopside and Hedenbergite. Understand? To accommodate more iron and magnesium to that series, calcium has lost some partial amount. That's why, because you know everything has to be compensated with these site assignments, right? So if you need more iron and magnesium, then you have to remove some calcium from this X site and give space for this iron and magnesium. That's why iron and magnesium come into this X site also, right? Otherwise, iron and magnesium is definitely is mainly accompanied by Y site. But since this particular ogite composition needs some more iron and magnesium, there is no space in Y site. only possibility is to remove some calcium and give space for iron and magnesium. Okay, so that's why this excess iron and magnesium comes into X structure, X site. Okay, so this is how these compositions are, these structural arrangements and chemical arrangements are made, right? Okay, so this is the pyroxene, clinopyroxene compositional diagram, where you see one particular series, that is diopside Hedenbergite series. So this is a complete iron magnesium solid solution between diopside and Hedenbergite. Okay, because iron magnesium completely solid solution series means here you see the magnesium end member and here you see the iron end member. In addition, what you have is calcium. So that's why it's located somewhere here in the middle part, because there should be calcium composition also. If calcium is not there, then it should go somewhere this level. Okay, if no calcium is there, you can see there is another series like that also, right? We'll come to that later. Okay, so augite or augite, sometimes it's pronounced as augite, but I prefer pronouncing it as augite. Some people pronounce augite, some people pronounce augite, right? Augite composition, as I mentioned, it has more iron and magnesium there. So in addition, you see what you have is sodium is also accompanied there to some extent. So how can sodium come there then? See, sodium is X site, right? Sodium is X site. So X site, you have sodium there to some extent, not that much. Okay, because sodium replacement into pyroxene site is happening under specific conditions. That means, to crystallize these minerals, pressure and physical conditions, pressure and temperature are also very important. So if the particular tectonic situation in the Earth's interior is favored with high pressure conditions, then sodium can easily accommodate there. Otherwise, if high, that means otherwise means high temperature conditions, right? If no high pressure conditions, then there may be high temperature conditions. Then rather than having sodium, calcium, iron, magnesium, all like to replace into these structures. Okay, high to moderate temperature conditions, calcium, iron and magnesium are the dominant ions which replace into pyroxenes. But in under high pressure conditions, sodium, iron and magnesium are the ones which prefer. Actually, sodium and calcium differs with respect to pressure or temperature. That you have to keep in mind, right? But later on, we will come into a very high pressure type of pyroxenes, very typical type of pyroxenes to discuss, which are having high sodium contents later on. Okay, right. For the time being, we are talking about the pyroxenes which are crystallized under high to moderate pressure and temperature conditions, right? Not high pressure conditions. So our rocks, the rocks we have in Sri Lanka, Madagascar, in southern India, Australia, like Brazil, like Canada, like those continents, right? Those are very old cratonic blocks. They are very old parts of the continental crust, right? They were formed in long time ago, more than 550 million years ago, right? Even in the Archean times, some parts of those terrains are produced. They were subjected to high temperature conditions. That's why we have high temperature type of rocks, right? Under introductory petrol, very soon, maybe 2 weeks later or so, you will learn about these differences. I think you may have received an email from Dean sir that your semester starting point has been postponed by 1 month or so, right? Probably you might receive it. Okay, so your second semester will start a little late, uh, since I think there were, after you had a meeting with the dean recently, right? So after that, anyway, so you will learn soon anyway under introductory petrology. Right. So augite composition, you can see here calcium, sodium, magnesium, iron, everything is there. Okay. So that's why you can see it's having a little bit broader region here just for augite. So it is closely related with diopside Heidelbergite series and addition of aluminum and minus sodium substitution, right? Minus sodium substitution. Aluminum is anyway there for any pyroxene, you know, aluminum is already there because it comes replacement with silicon. Okay. For any pyroxene, you must have aluminum, right? So it's not a big deal. But this sodium thing is important, right? Minus sodium substitution is important for oogyte. Okay, right. Okay, right. Now, is it clear? This particular two compositions, diopside Heidelbergite series and oogyte series. Oh, it's not series, oogyte composition, right? Any question? Do you have any question? Please put your numbers in the chat box to mark the attendance. So if you have a question, you can just post me now. Yes, someone has raised hand. Any question? Please talk. You can talk now. Any question? So I hope you got it clear. Okay. Right. So I will continue then. Okay. Right. So we considered the composition where mainly iron, magnesium, and calcium, all three which are present. But you remember this blank area in this triangle, in this blank area, usually there are no compositional pyroxenes found in the natural environment. That also you have to remember, right? These unshaded areas in this triangle represent uh, non-existing compositions, right? There are no pyroxenes existing, but there are some natural occurrences of this composition, this particular composition, right? So I will come to that later on, very late to in this lecture series. And keep in mind, this extreme calcium composition is found in natural environment, right? But it's not usually represented in a pyroxene triangle by giving a mineral name, but there is a mineral name there, right? But you can't see it here because we are mainly focusing on pyroxene group. That particular calcium composition we do not usually take into account as a pyroxene composition, right? But there is no harm to take it as a pyroxene composition, but there is a small structural difference in that particular composition, in that particular mineral. That's why we are not taking it in under the pyroxene. But some cases in the literature you might see that also has been taken under taken as a composition under pyroxene, right? But we will come to that later on, right? Now we considered these three components: iron, magnesium, and calcium composition. So I said, if calcium is zero, right? If calcium is zero, so this is calcium. If calcium is zero means your composition should be rich in iron and magnesium. Iron and magnesium rich means you must take it here, right? Because along this slide, because calcium is zero, calcium is starting from here onwards. 0, 1, 2, 3, 4, 100, right? When it comes to here, 100, right? Zero means here. So there are some pyroxenes which are falling along this line as well, right? So you can see here that composition is shown here, this particular series, okay? That pyroxene series, we have one end member as N-statite, okay? Magnesium rich end member as N-statite, and iron rich end member as ferrocylite, okay? N-statite, ferrocylite is another series. So N-statite and ferrocylite, which are purely magnesium and iron rich. No calcium component is there, right? So unlike Hedenbergite, you had calcium also in addition to magnesium, and also ferrohedenbergite sorry, diopside and Hedenbergite. So I'm sorry, diopside and Hedenbergite. Sometimes it's referred as ferrohedenbergite also, right? But just Hedenbergite is enough. You have calcium also in addition to iron, right? That's the difference. So that's why we call it clinopyroxenes. Okay, and here you have enstatite and ferrocylite series uh, where you don't see any calcium component. Magnesium is there, iron is there as the end members. Okay, no calcium means it's a different pyroxene then, right? So these pyroxenes are crystallized in orthorhombic system. Okay, these are crystallized in orthorhombic system, and therefore they are called orthopyroxenes. Okay, the previous pyroxenes which had calcium were crystallizing under monoclinic system. So that's why we call them clinopyroxenes or monoclinic pyroxenes. So these are orthorhombic pyroxenes, or we call them very easily as orthopyroxenes. So you now understand CPX and OPX compositions. Okay, in OPX compositions you don't have any calcium, and CPX you have essentially calcium component. Okay, definitely there must be calcium component in clinopyroxene, but orthopyroxene you don't have calcium composition, right? So magnesium end member and iron end member without calcium is there, right? So we have enstatite and ferrocylite, and in the middle you can see this composition, special composition is there, which we call this particular composition, right? This one we call pigeonite, right? It's a special composition because there is a little bit bulging towards calcium side, right? This orthopyroxene, actually it's not an orthopyroxene, and also it's not a clinopyroxene as well. But since it is having calcium component, particularly people tend to categorize it under clinopyroxene. Okay, but the calcium amount is not as rich as typical clinopyroxenes, which you have in this level. Okay, but still, since it has a great abundance, greater concentration than normal or typical orthopyroxene range, people used to classify it also as a clinopyroxene, but it's sort of in between ortho and clino, right? It doesn't matter, but you just consider it as a special pyroxene. And also the formation of pigeonite requires very special conditions. That means very high temperatures, right? And also it crystallizes in monoclinic system, so no harm. You can call it a clinopyroxene rather than any orthopyroxene. Okay. And we call there is a miscibility gap. Sorry, miscibility gap. What is miscibility gap? Miscibility gap. Or in other words, we call O-guide, right? Because you see, for to pigeonite, the closest clinopyroxene composition is O-guide, right? Not diopside or Hedenbergite, right? But still, you don't see any composition. I mentioned that white areas in this diagram are non-existing pyroxenes, right? There are no natural pyroxenes are found. So in between pigeonite and O-guide, there is a gap, right? So that means there is no natural pyroxenes crystallizing in that range. Not only in that range, actually, even here, no pyroxenes are crystallizing. Okay, and here also no pyroxenes are crystallizing. So these blank areas, so we call them miscibility gaps, these blank areas, because when you pass this miscibility gap, you encounter another composition. Okay, even here, if you pass this one, you encounter some composition here which is naturally existing. So that's why we term it as a gap. It's a chemical gap, right? Chemical gap means usually why we call it miscibility gap. What is miscibility? The term itself. Anybody knows it? If we say A and B are not miscible or immiscible, miscible. What is miscible? MISCIBLE. Miscible. Anybody knows it? Another, oh, can you present a synonym for that? Miscible or miscibility. What do you mean by that? Dissolution. Yes, one says dissolution. Yeah, close to that. Yes, it's correct, but not exactly. Yeah, in one hand you can say it's a dissolution. Another one, another term, more closer to miscibility or miscible. Very good. Yes, I got one. Mixing. Yeah, another one, another person. Yeah, both of you. Lahiru and Nilanka. Oh, Nilanka, I don't know. Mixing. Yes, that is the correct term. Mixing. They are non-mixing, right? Uh, that's why you have a gap there, right? They cannot be mixed together, right? So they are non-mixing, right? Miscibility gap is there, right? So, or other words, you can call it immiscible. They are immiscible, right? Immiscible, right? So this miscibility gap is there. So this miscibility gap is there. That means they are not mixing together, right? Mixing together means under solid state conditions. So we talked about solid solution. Okay, solid solution we talked about, that is mixing under solid state conditions. So these two compositions do not mix each other. That's why you have two groups existing as orthopyroxenes and clinopyroxenes. Okay. Usually, this we were talking about pigeonite. So this pigeonite, the composition is this one: calcium, magnesium ion, and so you see two magnesium here, one magnesium, and here another magnesium, and another ion here, another ion here. Why is that? Why we have separated them into brackets? Any idea why we do that? That's this. Okay, some iron and magnesium belong to X crystallographic site or M2 site, and some iron and magnesium belong to Y site or M1 site. So that's why when you write the formula, we separate them, right? This is the correct way of writing formula, because you represent the crystallographic sites as well. Otherwise, you could have written this as calcium Mg2 Fe2, like that, something like that, right? As a composite formula, right? So it's not like that anyway. So pigeonite is a special composition. Actually, it needs high temperature conditions. So there is a diagram here. We call a phase diagram, this one. So you will learn about phase diagrams later on. And in this phase diagram, you can see the temperature axis here. At higher temperatures only, this pigeonite crystallizes. Augite and orthopyroxenes both crystallize under low temperature or moderate temperature conditions, you can see here. Okay. Both clinopyroxenes, typical clinopyroxenes and orthopyroxenes are crystallizing at moderate to low temperature conditions, but pigeonite needs high temperature conditions. So what happens if the rock undergoes low temperature conditions when pigeonite is present? Right, the rocks can undergo pressure temperature variations, right? Sometimes they are subjected to high pressure temperature conditions, sometimes low pressure temperature conditions, sometimes from low temperature or low pressure to high temperature and high pressure. They can physically move. So that's what you call the subduction, collision, and all those tectonic things. Okay. So depending on those dynamic processes prevailing in the Earth's interior, these pressure and temperature conditions vary in the rock layers. Okay. So anyway, if pigeonite is present when it is subjected to lower temperature conditions, what happens is this pigeonite becomes unstable, because that is stable under higher temperature conditions. So unstable means they break down into other forms. So you have pigeonite because the closest composition to pigeonite is augite, right? The closest composition is augite, so it can convert into augite, right, under low temperature conditions. So when it is subjected to low temperature conditions, what happens is Pigeonite dissociates into ojite plus OPX. Some other OPX is there, right? So ojite plus OPX. One of the OPX is either enstatite, ferrocylite, or a mixture of it can be found, right? So this happens in igneous rocks mainly, not in metamorphic rocks. But this happens in igneous rocks mainly because in igneous rocks you have sufficient amount of iron, magnesium, calcium, and everything freely available. In magma, igneous rocks means the rocks which are crystallized from magma. Okay. So shallow intrusive igneous rocks. Intrusive, you will learn about these intrusive, these terms under introductory petrology, under the igneous petrology part. So these are shallow rocks, shallow igneous rocks. Okay, so they dissociate into ojite and OP. So the opposite can also take place when the temperatures are increasing. If you have ojite and other pyroxenes, orthopyroxenes in a rock, they can react to form pigeonite. They can react to form pigeonite in rocks. Okay, understand? So if you have any question up to this content, please let me know now. Okay, no questions. I don't see anything in the chat box also. Okay, so I hope you can understand it clearly, the content. Okay, shall we proceed then? Okay, right. Before going to that section, now let me go back to the composition of this typical composition of pyroxene. Okay, here. So I said in this case, the sodium is not very commonly accompanied into the pyroxene structure, although it is a compatible element. That means it's a fitting element or fitting ion to the structure. It needs some special physical conditions, I said. Okay, physical conditions. So what is the physical condition that you expect? Pressure and temperature. Okay, so under high pressure conditions, what is happening there is sodium can be preferentially incorporated into the pyroxene site. Pyroxene site, sodium can be preferentially incorporated into. Okay, so let's see. Right. So those type of pyroxenes we call sodic pyroxene. So it's a separate group. So that is why I said that it's a separate group, right? Sodic pyroxene. So in these sodic pyroxenes, sodium component is pretty high, right? Under high pressure conditions, that means in subduction zones mainly, right? In the Earth's subduction zones, the oceanic plate is subducting beneath the continental plate, right? So when this protolith or whatever the sediments or whatever the materials which are being subducted, if they have sodium component, aluminum, silicon is usually there in sediments, right? And iron magnesium is also there. So they prefer to form a special type of pyroxene that is called sodic pyroxene. So these sodic pyroxenes, predominantly you have sodium and aluminum. And if you go back again to the structure, so even aluminum is a predominant composition there than the normal pyroxenes, right? And sodium become more predominant than iron, magnesium, and calcium, right? Because usually what we observed was iron, magnesium, and calcium as the main composition for pyroxenes, right? See, iron, magnesium, and calcium as the normal pyroxenes under moderate pressure and temperature conditions. But under high pressure conditions, sodium becomes very dominant. Sodium become very dominant, and that's why you have this sodic pyroxene. So it's a special type of pyroxene, and one such mineral is jadeite. Okay, jadeite is one such mineral. So there you have another series formed, solid solution series, like you had for other pyroxenes like enstatite, ferrocylite, or diopside Heidelbergite series. Like these are solid solution series because your replacement, iron, magnesium, calcium replacement is happening in the solid state conditions. So similarly, under high pressure conditions, sodium becomes a dominant phase, and which replaces with iron, right? So you have one end member as jadeite and the other end member as a mineral called agerine. Okay, agerine is the agerine. You have sodium and ferric, not ferrous, right? Previous cases we had ferrous, Fe2 plus. This is Fe2 plus. Okay, so already ferric can also come into the structure, right? Ferric can also come into the structure instead of iron, magnesium there, right? Chromium can also be there, right? Ferric, chromium, titanium even can be there, right? So under high pressure conditions, ferric and sodium is coming into the structure, right? So they form a solid solution series uh, called jadeite and agerine series. So you have jadeite and agerine series here, right? So up to 20% of maximum the other components, but sodium and iron have predominant compositions, right? Because here sodium 100%, here ferric 100%, but some sodium is also there, right? So that's why you have sodium there, but you can cut this sodium out from this composition, right? Because you are now in the agerine side. The 100% ferric should be there in the agerine, right? Minor sodium can be there, it is essential, but you can ignore that for the time being, okay? Because you are now in the 100% agerine series. But since the sodium indication is there, you should understand that 100% ferric never accommodate into pyroxene structures. Okay, at least 1% maybe, or 0.5% to 1% should be sodium. That's why sodium is indicated there, unlike in previous cases. Ferrous 100% is there, right? It's ferrous. Okay, no magnesium term in this one, right? But here you have the sodium term also, that is coming from this side. Okay, that means a very tiny amount of sodium can also be is also be there essentially in natural environments, right? So that's the point there. So jadeite agerine series is one sodic pyroxene series, and also you have uh, another series that is moderate composition. That means around 50, right? This is 50, around 50 line. Okay, so you have another mineral called omphacite. Actually, this omphacite can be variable up to this range. Omphacite, agerine, augite. The other one is agerine augite, right? It's not agerine, it's not augite. It's agerine augite. Okay, so you have another broad range of minerals, right? So you can consider it as omphacite agerine augite series, like this. This series you can consider as omphacite agerine augite series. So all these are sodic pyroxenes. All these are sodic pyroxenes we refer here, right? So here, actually, this in this part, only you have this calcium, magnesium, iron pyroxene. So that means you can replace entire this triangle, right? Entire this triangle is magnesium, iron, calcium triangle, right? So that is here. Magnesium, iron, calcium triangle, it's here. So all the calcic pyroxenes, we call calcic pyroxenes to those pyroxenes, are here. And beneath that, you have this sodic pyroxene. So that means you have calcic pyroxene triangle here, and below that, you have sodic pyroxene triangle. But this is only available in high pressure rocks, right? So the high pressure rocks, that indicates predominantly you have sodic pyroxenes and very less amount of calcic pyroxenes are there, right? But in other rocks, that means high temperature or moderate temperature rocks, you have predominantly calcic pyroxene group and a very little amount of sodic pyroxene is there. Okay, like that. This is how this calcic sodic pyroxene variations are happening. For high pressure conditions, what you need is, what you see is sodium replacement rather than iron, magnesium, or calcium replacements. Okay, so jadeite is a very common composition, and jadeite is produced in igneous rocks by a special mineral called nepheline. Okay, you may have heard of this nepheline, I think, probably, but anyway, you will learn about these things under igneous petrology in third year. There is a mineral called nepheline, and it reacts with albite. What is albite? It's a feldspar. Okay, one type of feldspar. We will learn it later on. Okay, that forms pyroxenes, jadeite composition, right? Albite is sodium-rich feldspar. Okay, nepheline is sodium-rich, another mineral, silicate, that produces jadeite composition. So that is a typical composition, or in other words, albite, that is a feldspar, reacts with quartz, right? Quartz, you know, SiO2, to form jadeite. That is also possible under high pressure condition. When the rock is subducted to deep levels, right? Whatever the sediments you have with feldspar, quartz, right? These sediments are there, right? So when they are subducted, they are also brought down, right? So then they become unstable and produce new minerals, right? New minerals are produced under this stage. That means high pressure stage, right? Very depth, very deep interior. Okay. So omphosite and all these minerals can be formed in the different reactions. In different reactions, you can find these ones. Okay. Right. Now, these are the sodic pyroxenes that you can find in rocks. Okay, understand? Right. So we call sometimes, right? As I mentioned, not only in sodic pyroxenes but in calcic pyroxenes also. Calcic pyroxenes means the pyroxenes that we have been talking about in previous cases, clinopyroxenes. These sodic pyroxenes are also part of clinopyroxenes. Okay, they are also monoclinic, and some are orthopyroxenes. Okay, yeah, that I have to tell you. Omphosite is a orthopyroxene type, right? It's a orthopyroxene type. So being calcium is absent, they can be considered as orthopyroxene easily, right? So it's a little bit complicated, but anyway, you will learn more details about these things later on. But for the time being, you just keep in mind that these are sodic pyroxenes, right? So these cations can be replaced in a mixture of settings, right? For example, monovalent cations, because sodium is monovalent, and trivalent ferric. We said that this is ferric, this ion. So they substitute to the structure at once, right? You have sodium substitution, and at the same time you have uh, ferric substitution. That means monovalent substitution and trivalent substitution. But previously, what you had was ferrous or magnesium like substitution. Calcium, all are divalent cations, right? No difference. But here, valence is also different, but substituting at the same time. So therefore, we call it coupled substitution, right? Two substitutions are taking place under solid solution condition or solid state conditions. Okay. So therefore, we call coupled substitution is happening in particularly in the sodic pyroxenes. Coupled substitution. Uh, Different valency ions are substituting into the structure. Okay, so coupled substitution can take place even here if ferric is substituting, right? If ferric is substituting together with iron or magnesium divalent cations, then again in this calcic pyroxene also you can expect coupled substitution, but it happens rarely. But in sodic pyroxenes, it very commonly happens. It very commonly happens. That's why I told you that there are no 100% ferric pyroxenes. There are some monovalent cation also substituted into the structure. Okay, right. Do you understand? Any questions? Did you get the point clearly? Right. If you have any question, you can ask now. I can give you 1 minute, or you can just type in the chat box also. So after this, I have only one more lecture to take for you. So we will try to complete it in the next week. This descriptive descriptive mineralogy part. Okay. Right. So if no questions, I think we can conclude for today. Are you sure? No questions? Everything is clear, crystal clear. But in the exam, you might have problems, right? So you have to review the content we have been talking about so far, and be thorough also with some extra readings from the internet for the time being, because you don't have access to the libraries. There are very good textbooks in the library. You must refer that as soon as you are allowed to come to the university. Okay. Right. So I will stop here for today then. So have a nice day. So we'll meet next time.